All right. Well, good morning, everyone. It's good to be back with you. We are going to introduce a new kind of integral today, uh, the, the line integral. And in some ways, this will be relatively straightforward. As usual with many of our integration examples, once things get set up, it'll just be a little bit of crunching. But conceptually, this is interesting because our applications are oftentimes a little less visible. We're going to be setting up line integrals to evaluate work or to calculate work, which isn't something that you can taste or touch. It's a little bit more abstract than that, and so it requires us to apply kind of the concepts that we know from earlier in calculus about integration, but also about work and things from physics, and then sort of make a connection that's happening more in our head than with our eyes. All right, so today we're going to talk about line integrals. This is the beginning of section 17.2, and there's three main topics in this section. So we're going to be talking about scalar line integrals in 2 and 3 dimensions. We're going to talk about line integrals across vector fields, and these let us calculate work. So it's work to calculate them. Lots of good jokes here. And then the last topic is we will introduce the concepts of circulation and flux. And so in some ways, this section sort of gives you a backdrop of where things are going for much of the rest of the quarter. So in previous sections, or in previous chapters, we considered 3 kinds of integrals in rectangular coordinates. We talked about single integrals that were over intervals, double integrals that were over 2-dimensional regions, and triple integrals that were over 3-dimensional regions. In this section, we shall discuss line integrals, which are integrals over curves in 2 or 3-dimensional space. Integrals over curves were invented, or maybe that was discovered, in the early 19th century to solve problems involving a variety of things such as fluid flow, force, electricity, and magnetism. The application that's easiest to visualize is the surface area of a curtain under a surface and along a curve C on the XY plane. And we're going to start our introduction there. So in order to unpack this surface area, is my connection poor? Let me mute my video, which is probably a better look for me anyway. Hope that that's better. So in order to unpack this idea of surface area, we're going to start by trying to understand what's going on with parameterization. Is the connection any better now?
Yeah.
Okay, so we'll go to the screen share. I'm not sure what that will do. All right, is that clear for everyone?
Yeah.
Okay, thank you. So in order to unpack the surface area, we need to parameterize the curve C, which requires that we distinguish between the parameter T, which is not visible on the graph, and the arc length S. So we're going to talk about parameterization for a moment. Okay, so I want to point out that when you parameterize, you have this graph here that's in terms of X and Y, and this is visible, like something that you can see. But then there's this parameter T that lives outside of the visible world, which is sort of dictating what's happening with the XY visible world. What's our most common application or understanding of T?
Time.
Yeah, so we think about T as being the time, and you can't see time, but it is taking place and it's impacting things in the XY world. And so you can imagine that the number of subintervals in the T world, so here's notice these are all equally spaced. that all these t subintervals are the same length. So while the intervals in the t world are the same length, you can see that maybe this subinterval here, maybe I'll label it 1, sure looks longer than subinterval 2 over here in the xy world, right? And certainly it's true if you look along on the x in between x of t1, x of t2 versus x of t6 and x of t7. So the delta t's, if you will, are invisible. You can't see them. It's like a change of time. But a delta x or a delta y would be visible. And so what we're going to do out of all this is we want to see the connection between the delta t's, or what's happening in the t world, and delta s. You remember what s stands for in most of these applications?
Displacement?
Displacement, or in this case, it's going to stand for arc length. And I think that there's no s's anywhere in arc length as nearly as I can tell, but maybe my personal theory is that we use the letter s because it's like an arc. It's got a nice curvy look to it. That's my personal theory for why we use s. So delta s here would be talking about the arc length of this curve between the 2 points. Do you remember how to find arc length in general?
Integral of the square root of something squared plus something squared?
Yes, or like an x prime squared.
I always just call it magnitude.
Sure. Sum of squares, and then we have usually like a dt or a dx or something like that. Is the connection any better now? Is it working out better for people or no?
Everything's okay on my side.
Okay. Very good. You just didn't want to see my face. You should have just said it directly. Okay. All right. So everyone okay with this idea that there's this parameter t that you can't see? We've talked about parameterization many times, but then there's also this curve, and specifically what we care about is the arc length. So far, so good? Very good. All right. So with this in mind, we can define and calculate the scalar line integral in the plane, which represents the area of a curtain under, and I say under because maybe it's actually got, maybe it's the wrong, maybe the thing actually lives underneath the xy plane. So anyway, under the function f and above the xy plane along the curve C. And I think I have a picture of this coming up. So let me switch to the picture before going to that definition. Okay. So here would be our curtain. So notice that the curve, the curve along the base, this right here along the base, that's our C. And then the red at the top, this is coming from z equals f of xy. So it's the curtain, and you can sort of see the little panels. It's the curtain underneath f and above the xy plane following path C. Can people visualize that?
So is this kind of like a bounded plane of like a curve?
Like, it's it's like you have some curve and we want to know what's the, well, let me backtrack. My wife and I went to China a few years ago and we got a chance to go to the Great Wall of China, which is unbelievable. Like I don't usually get blown away, but the Great Wall, one of the things that struck me from the Great Wall is that you have this wall that is literally thousands of miles long, and it winds around kind of like a snake, over hills and et cetera, et cetera. And the height of the wall varies. Sometimes, some places it's really low, some places it's really high. And I think I was looking for Mulan, but I didn't see him or her, or maybe that was the wrong movie. But anyway, but if you wanted to find the surface area of the Great Wall, you would have to track both kind of the path of the wall, and then you'd also have to track the height of the wall at any given place. And so in some places the wall is really short, in other places the wall is really tall, in some places it's mostly collapsed. And so you can imagine that we could take that wall and we could break it up into a whole bunch of little rectangular regions, and like we've done over here, to figure out an approximate area for the wall. I think that was Damon asking the question earlier. Did that answer your question?
Yeah, thank you.
Very good. Okay, so if we want to calculate this area, then we could simply increase the number of partitions, right? And so more rectangles is going to give me a more accurate approximation. We've done this many, many times. And notice, in order to find the area of each partition, you need to know the height. And the height is pretty straightforward. This is going to be given by our function f, but you also need to know the length or the width of the rectangle. And in this case, the width of the rectangle is given by an arc length. Make sense?
Whoa.
So you're going to end up with a whole bunch, the area of a single rectangle is going to be the height f times the arc length delta s. Questions? By the way, you guys are all very kind on my face. Very good.
I think I have a question.
Go
So
ahead.
our function f of x, y, is it always on top of that arc length, or will we ever have it like stretching a little bit more one way? Is it like always on top of it? Because I see that curve is like.
So I think, good question. So I think what's a little interesting here and hard to see is that z is equal to some f of x, y, and it creates a surface. So in 3 dimensions, just like we've been looking at for the last quarter and a half. And then below you have some c, and then we could ask, well, what happens if we follow c up onto the surface? And so on here, you're going to have that red curve is following this three-dimensional surface, but it's only showing the three-dimensional surface that's immediately above the C.
Great visual. That did it. Thank you.
Did that do it?
Oh, yeah.
Other questions? Very good. So in terms of actually working through it, I think you should now see that if we wanted to find the total area, we would have this height here. Here's my F, and then here's my delta S, my width, my arc length, if you will, and we're going to sum them all up, and that's going to give us an approximate area. And so if we want to make sure the area is exact, we'll take the limit of those Riemann sums, and that will get us to the definite integral, but it's a new type of integral. Notice we now have this little c down below, because what we have is a line integral. So it's a line integral, and instead of having a dx or a dy or a dA or a dv, all the other d's that we've had, now we have the ds. And what does ds represent?
The arc length?
Represents the arc length, exactly. So the differential arc length, yeah. Questions about where this formula comes from? Very good. All right. So we already looked at our Eeyore picture. And so the key to applying this formula is to find a formula for the ds. The ds is the punchline. So to do this, recall that if a space curve is parameterized by r of t, then the cumulative arc length of c over the interval a to t, there's a little bit of subtlety here. So this is a to t, is s of t equal to the integral from a to t, right there, of the magnitude of r prime of u du. Why is it, remind me how you find the magnitude of r prime of r prime. So like r prime would be like x prime, y prime, like that. And so its magnitude would be the root of x prime squared plus y prime squared. It should look familiar because I think that was roughly the formula that Enrique gave us a few minutes ago. And so S of t, the cumulative arc length formula, would be this definite integral for going from a to t of r prime of u magnitude du, and here the u is a dummy variable. And we can differentiate both sides using part one of the fundamental theorem of calculus, giving us that s prime equals the magnitude of r prime. This would be like saying ds dt. And so if you multiply both sides by dt, you'd get ds equals the magnitude of r prime of t dt. Questions about where this formula came from? Very good. All right. So we did all that work trying to get to some formulas. So here's your formula or formulas. They look super intense and scary at first glance. You're like, man, can we get some longer formulas? These ones are long. Let's start by noticing the difference that in the first case we're in R2 and you have X and you have Y. And then in the second case, we're in R3, and you have X, and you have Y, and you have Z. So the formulas are analogous to each other. I would encourage you to just focus in on R2. This is what I'm going to do throughout our notes as much as possible, knowing that we can always add a third dimension if we need to. It's just not that big a deal to have 3 dimensions, except for it makes the formulas longer. So what's going on here is that we have F. This is our height. So all this stuff is the height. And then the R prime of t magnitude times dt, that's our ds. And magnitude of R prime is a little bit complicated to use, and so, ew, that's a terrible color. So this thing right here can be simplified or expanded out into the more easily usable formula, root x prime squared plus y prime squared. Questions? All right. Guessing about now, you're thinking to yourself, gee, could we do an example with this? Like, I'm not really tracking what's going on here. So let's switch over and see whether the live camera is working again. Work an example on the doc cam. All right. So we want to find the surface area above x squared plus y squared equals 1 and under z equals 1 minus x squared. So our first step is to parameterize. So what do we need to parameterize this part, the x squared plus y squared equals 1 part. So how do you parameterize that circle?
Cosine of t, sine of t.
Cosine t, sine t, and whenever we parameterize, we also have to give where the parameters live. So where do the parameters live?
0 to 2 pi.
0. Thanks, Jay.
2, 2, 2. Yep.
Okay. So step 1, we parameterize. Yay. Easy money. Step 2, we're going to find our ds.
So did we basically just put it into cylindrical coordinates?
Not really. We haven't changed coordinate systems. All we're doing is we're parameterizing a circle in this case. We're parameterizing it's like we're parameterizing the base of the wall almost. Yeah, so I don't think it's not really cylindrical or polar coordinates.
It's basically just convert x and y into t.
Yeah, convert x and y into t would be a better way of saying it. Because notice if you had, if you were in polar coordinates or cylindrical coordinates, you might have a t, but you would also have an r somewhere in. You'd also have an r in this, and so there's only one parameter, not 2 parameters. So our formula for ds, good question. I think that was Croy, so good question. So ds is magnitude of r prime of t. And so it looks like we're going to need to know what is r prime of t. So r prime of t looks like negative sine t cosine t. And so the magnitude of r prime of t equals the square root of sine squared
1
a square root of cosine squared, or just 1. And so we get that ds is equal to dt. Questions so far?
Wait, so why did we do the whole second step? Is that so we could figure out that ds is equal to dt?
Yeah, we need to find that ds is equal to dt. In this particular example, it's not very exciting because our answer is, our scaling factor is 1, but it won't always be that straightforward.
Okay.
Yeah, good question. All right, so step 3, we need to substitute in for x and y and integrate. In the integrand, okay. So let's see how this works. So our surface area is going to be the integral along C of f ds. So we parameterized. Our parameter is going from 0 to 2 pi. Our f, that's the 1 minus x squared. Okay. So we're going to have 1 minus, and then what is our x? Do you remember?
Cosine t.
Exactly. So this will be cosine squared t. Okay. And then ds is going to be 1 dt. Let me just highlight. And at this stage, it's just an integration. So we need to find an antiderivative of all of this stuff. So this would be 0 to 2 pi of sine squared t dt. And we have to use our half angle identity. Is this 1 minus cosine 2t?
Yeah.
Get my signs right. So we're going to have 1/2 theta minus 1/2 sine 2t from 0 to 2 pi.
Why do we have a theta?
Antiderivative of 1 is theta.
Why isn't it?
Oh,
Should be f.
got it. It's a letter thing. Like I said.
I thought you broke math.
I was so confused.
Yeah, so we have a t. Okay. Actually doesn't look too bad. Now you know the truth. What's the difference between t and theta? T is half of a theta. Okay, so we have t minus 1/2 sine 2t from 0 to 2 pi. Notice that at 0 and at 2 pi, the sine part will be 0, and so we're just left with pi at the end of the day. What does this pi represent?
Surface area.
Yeah, so this is our surface area. Very good. Questions about this? Very good. All right. So it looks like I have the same the same issue with my thetas and t's here as well. But the important thing is to know that this area represents a surface area. And specifically, if you go back to the picture on the handout, it would be the surface area of this wall. It's kind of circular, but under this curved surface. So this is our first application of a line integral, and probably the easiest thing we'll get to visualize for the rest of the quarter. I hope that's not too bad a news. So a couple of important notes, actually a whole bunch of important notes. And I just want to highlight two of them in class. The rest of them are here in writing. So the first is starred, and that's just talking about the procedure that we used. So the first thing we did was we parameterized. That was step one. The second thing we did was we found our ds. And the third thing we did was we substituted in and we evaluated. So that's kind of the process that we were going to use. What we are, like the specific formulas we're going to use are going to vary from application to application. But this general pattern of parameterizing, then finding something related to a differential, and then doing a substitution and evaluating is going to happen over and over and over again in this chapter. The second thing I want to highlight is the second star, and that is that probably the most challenging part of this this chapter for students, at least in my experience, really is in the parameterization. So the most difficult thing is parameterizing, and obviously it could be very difficult, but there are two really common scenarios that it's worth becoming really comfortable with. And so the first is a line segment, and the second is a circle. Here, notice in the circle, what I did was I centered the circle at AB, and I gave it its own radius. So this would be a circle centered at AB with radius R. In the example that we were just working on, AB would have been 0, 0 because we were centered at the origin. R would have been 1 because we had the unit circle. But those are two really common parameterizations. They won't cover everything, but they will cover an awful lot. Now that I think about it, maybe I would add one more, and that would be a function, something like y equals f of x. And if we have something like y equals f of x, what would your r of t be? So if you, in this case, we would say that our independent variable is x. And so we would let that be our, we would let t represent x. And if t represents x, what would the y value be?
F of t.
F of t. So I think we've got an example in a few minutes or later on in the section where we have y equals x squared as our defining our c. And so in this case, we would have r equals t comma t squared. Questions about this?
Just say x equals to t, and so y equals to t squared, right?
Exactly. Yeah. Yeah. The only other note here, it's not a difficult one, but the only other note here that's probably worth paying special attention to is that if you have some system like we have up here in this earlier bullet point where there's multiple chunks, you can break it up into multiple parts. And so we could find the work along C1 plus the work along C2 plus the work along C3 plus the work along C4, boom, plus the work along C5. This one, the work along C3 is followed by PO, but there's work for C3PO, et cetera, et cetera. Not difficult, but nevertheless worth commenting on once. Questions before we go on? Okay, let's do another derivation. So I told you that our big application that we're going to work with is the application of work. And if you've been coming just through calculus, then you probably would have had a few examples with work. If you've had physics or engineering, then you probably had lots of work with work. But the short version is that we like to think about work as equaling the force times the distance. Equals force times distance. But force times distance is kind of just day one about work. What we really care about is the amount of the force that is tangential to the direction that the object's moving. And so, the classic examples are things like, maybe you have a mass and we're going to pull it at some angle, theta, and we could ask how much work is taking place. And in order to find out how much work is being done, we would need to know what's the tangential component of that force. For those of you that have had physics or engineering somewhat recently, am I being kind of accurate?
Yeah, it sounds good to me.
Okay. Thanks, Joseph. So notice that the work only depends upon the tangential component of the force. Tangential meaning the object in this particular case is moving this direction, and you could split that force up into an Fx component, maybe, and an Fy component. And the only one that's going to impact the work would be that Fy, because it's tangential or in the same direction that the mass is actually moving. So work done by a variable force is the same thing. So if an object moves along a straight line from A to B subject to a continuously varying force, then we define the work as, again, F dot dx. And here you've got the F representing the force, and you've got the dx representing the distance, so to speak. That force.
Displacement.
Or displacement. Thank you. Going back a moment, what's the vector quantity that is really good at finding tangential stuff? Hint, it's right here.
FD cosine theta.
Yeah, the dot product is really good at helping us figure out what's the tangential part of whatever those two vectors are, how much are these two quantities parallel to each other. Questions so far? Very good. All right, so here's the new part. It's a lot of words. Punchline is really easy. So if an object moves along a smooth curve C through a continuous force field F, and so my force field, these are what we were talking about yesterday. So there's our F and our G defined in R2, and the work done is obtained by integrating the tangential component. There it is again. Tangential component of the force along the curve. So we have the force dotted with big T. So this is the same big T that you had last quarter in Calc 3, the unit tangent vector. And so F dotted with T will give you the tangential component of the force. And then the ds makes it a line integral, or because it's a line integral. And this particular definition would basically be expanded just to include a z, should you be in 3 dimensions. So at first glance, this looks super complicated, but work is actually straightforward to calculate, to implement. So recall that you have r equals xy, xi plus yj. Then you find that unit tangent vector by finding r prime divided by the magnitude of r prime. Okay, so things at first glance seem to get more complicated. So here's your work equals f dot t ds, and then we'll replace the t with r prime over magnitude r prime, and we can replace the ds with our formula for ds, which was magnitude of r prime dt. And good news, notice that you have an r magnitude of r prime of t in the denominator, magnitude of r prime of t in the numerator, and so you're left with f times dotted, don't miss that dot that's there, dotted with r prime dt, or we simply write that the work is equal to f dot dr, with dr equaling r prime dt. Questions? Very good. All right. Let's see if we can get one more example here. Maybe just looking at the time, let's look at my worked through version. So we want to find the work done by the force field F equals x cubed y I plus y minus, or x minus y j, on a particle that moves along the parabola y equals x squared from -2, 4 to 1, 1. So our first step is to parameterize the curve. We actually already talked about this a little bit. Since we're parameterizing y equals x squared, then we replace our x with t. As soon as you have x equals t, that gives you that y equals t squared. Anytime you parameterize, you need to say where those limits of integration are. That is, where does the parameter live? And so in this case, because your x is equal to t, your t values are going to range between -2 and 1. Questions about the parameterization? Very good. So step 2, we are going to find our differential element, find our dr, and notice the dr has the little arrow above it because it's a vector quantity. So dr dt would be the derivative of r. Derivative of t is 1, derivative of t squared is 2t. So dr dt equals this, multiply both sides by dt, and we get that dr is equal to 1, 2t dt. Questions? Very good. Step 3, we need to make our substitutions. And so we have our formula that the work is equal to the line integral of f dot dr. And again, this dot here is a big deal. You need it in order to take vector quantities and turn them into scalar quantities. And so my f was, I can't see it above, is it x squared y? think. And then here we have x minus y. So x, did I do that right? Am I remembering right? I think it's maybe x cubed. I think it's x cubed y. So remember, x is equal to t. So this would be t cubed times t squared. That's where the t to the fifth comes from. X is equal to t, y is equal to t squared. And all this stuff is our f. Then we come in here and we replace our dr with 1 comma 2t dt.
I'm a little confused on the substitution part for t.
Mm-hmm.
Like up in step 2, I think.
Okay. Right here?
Step 1, sorry.
The other two. Okay. Uh-huh.
So why does y equal x squared turn into t 2?
We think about how the parameterizations, kind of how this works. So if you have y equals x squared, this is the relationship. And so if we said x was equal to smiley face, then y would be equal to smiley face squared.
Okay.
Right?
All right, that makes sense.
So that makes sense. So does that answer the question for you?
Yeah, okay.
Very good. Cool.
So do we always set like x equal to t then?
If you're given a function like y equals f of x to describe your c, then most likely the answer is yes. Yeah. So you're usually going to have two scenarios. One scenario is you're given a graph, and in which case you just sort of have to recognize what's going on. The other scenario is where you're given a function to describe c, like this. And yes, in that case, letting x equal t will get the job done pretty well.
Okay, thank you.
I'm sorry, I'm still confused. Why does t go to 1? Like, where did the 1 come from?
So the t, so look at our x's here. So our x's are between -2 and 1.
Oh, okay.
But x is the same thing as has been replaced by t.
Right, okay, gotcha, thank you.
All good questions. All right, let's see if we can knock this thing out. So we've replaced our f.dr with vectors that are now all in terms of t. And notice that includes replacing our c with t values for our limits of integration. So notice that this thing that we're left with, this is like a math 152 integral. 152, like easy integral. You still have that dot product in there, so you have to take the t to the fifth times 1 plus t minus t squared times 2t, which will give you a nice clean polynomial. Integrate, evaluate, and at the end of the day, you get a number out. So what does this 3 represent?
Three power units?
Work.
This is work. What are the units of work? It's been a while. Is that
Joule.
joules? So like something like joules. So this is the work to move along, and I'm not going to write it, I'm too slow with my mouse. So it'd be the work to move along y equals x squared from -2, 4 to 1, 1 through the field x cubed y comma x minus y. So that would be how much work would be required. if the field described the flow in a river, then you could think about this as the work required to move your inner tube across the river from one point to the other point along the given path. Questions? All right. So I think based on what I'm hearing, yeah, I like that. Neglecting friction, mass, et cetera, et cetera, et cetera, et cetera, and assuming a spherical inner tube. So I think that what you can see is that the actual calculations aren't that difficult. But the big step that happens here is that parameterization step. That tends to be the challenge, just sort of keeping things straight. So as you're reviewing this lesson, as you're looking ahead, I would again encourage you to be comfortable with those, make yourselves comfortable with those parameterizations. They're definitely here to stay for the rest of the quarter. And so the more quickly you can make peace with them, the more fun you'll have. In the meantime, may you all have a wonderful day, and may all of your workloads be light and enriching. Thanks, everyone. Feel free to hang on the line if you have questions, but I look forward to seeing you all tomorrow. Take care.